You might not think about gravity much, but it affects everything we do. It's the reason why things fall down instead of flying up. It keeps us connected to the Earth, so we don't float away into space when we jump. But for physicists, gravity is something more. It's a fascinating puzzle that needs to be solved to understand how the universe works, and they're on a quest to uncover its secrets. So what's so mysterious about it? Let's see. We've learned a lot about gravity from the legendary Isaac Newton. He was the first to invent the law of gravitation. He taught us that any two objects in the universe can't help but be attracted to each other. It's like they have this secret gravitational crush going on. How strong this attraction is depends on two things: how big the objects are, that is their mass, and how close they are to each other. But here's where it gets cool. Gravity isn't just a two-object dance. It's a complex space choreography. Take our solar system, for example. The sun plays the lead role, using its gravitational pull to keep all the planets in their orbits. But each planet also has its own gravitational mojo, tugging at the sun and even its neighboring planets. Then, a few hundred years later, another hero, Albert Einstein, took gravity to a whole new level. He described the theory of general relativity. According to Einstein, gravity isn't just a regular force. In reality, it's curving and warping the fabric of space-time. Think of it as a heavyweight champion sitting on a rubber sheet. The sheet bends and curves under the weight, and the smaller objects nearby can't help but roll towards the heavyweight. Now, even though we can't see space's curves with our own eyes, we can see what happens to objects that get caught in its grasp. Getting pulled by gravity is like being caught in a whirlwind of forces. The caught object starts spiraling downward, just like a coin in those penny slot cyclone machines you find at tourist shops. Or it might move gracefully in circles, like bicycles racing around a velodrome track. Gravity is the primordial force that guides our entire world. Without it, there would be no stars, no galaxies, nothing. But where does it come from? Well, that's the million-dollar question. And we don't have a complete answer just yet. But we do have some guesses. First of all, we know that gravity is more than just a feature of space. It's a force that pulls things together. Surprisingly, it's the weakest force among them all. But let's take a different look at gravity. Something that may surprise you. Instead of being a force that directly pushes or pulls objects from a distance, it's more like a dance. Gravity, as amazing as it is, doesn't perform alone in this dance. It shares the spotlight with other forces, like electromagnetism, for example. Let's imagine two electrons. There are dancers. Now, they don't directly push or pull each other like you might expect. Instead, one electron creates a special kind of field around itself, like an invisible force field. This field sets the stage for the show. The other electron senses this field and starts to twirl and interact with it. It's like they're following some choreography. And when we watch this dance, it looks as if the second electron is being pushed or pulled by the first one. But in reality, it's all about the intricate movements and interplay between the dancers and the field they're dancing in. The dancers never touch each other directly, but their interactions through these fields make it seem like they're connected. It's a magical display of fields and movements coming together to create the illusion of forces at play. The thing we call gravity. So even though it's not a force in the usual way, it behaves like one. We call it an emergent force, because it emerges or comes out from the way space and objects interact. Which is why, if we want to get technical, some scientists prefer to avoid the words gravitational force and opt for the term interaction. It's just a way for particles to mingle and exchange energy and information. Electromagnetic interactions, gravitational interactions, they're all part of this grand soiree. At least that's one of the theories. Some scientists also think that gravity might be made up of tiny particles called gravitons. These sneaky particles work behind the scenes, making objects attract each other. However, we haven't been able to directly see these elusive gravitons yet. So, according to this theory, gravity is both a force and a potential particle. As you can see, we have some struggles with explaining how gravity works on a large scale. But at least we have a good understanding of how it behaves in certain situations, like how planets orbit the sun, or how objects fall to the ground and stuff. But what happens when we zoom into the atomic scale? And what if we venture into the depths of black holes and the Big Bang? Now here's where gravity's wild ride goes off the rails. First, let's enter the realm of quantum mechanics. There's something peculiar that happens in this tiny world. Gravity. The force that pulls things together seems to take a back seat. On a microscopic scale, other forces like electromagnetism take the spotlight and become the superstars. They're overshadowing gravity, and this leaves scientists scratching their heads, wondering, is this possible? Why does gravity suddenly fade away? So far, we have no idea. And when it comes to the grandest scales, where immense objects like black holes, gravity takes on a whole new level of complexity. For example, inside a black hole, laws of physics and gravity, as we know them, basically fall apart. It also decays when we try to understand how gravity behaved immediately after the Big Bang. Where did it even come from? We have no idea. In other words, we find ourselves in a cosmic fog when it comes to understanding gravity. But fear not, scientists are working hard to learn more about this enigmatic, emergent force. They're doing all sorts of experiments and using fancy technology to crack its code. Even though we still have a lot to figure out, we're making progress every day. For example, have you ever heard of gravitational lensing? It's like a mesmerizing magic trick. Imagine a beam of light as a fearless explorer, taking a straight path through the universe. But as it encounters the gravitational pull of a massive object, the light's journey becomes a wild roller coaster ride. The gravity of the massive object bends the fabric of space-time, creating a funhouse mirror effect. Our brave beam of light finds itself curving and twisting around the massive object, following a new unexpected path. But as the light changes its trajectory, it also reveals to us distant and hidden wonders that would have remained invisible otherwise. The light can magnify, distort, or even create multiple images of faraway objects. So all the things that have been playing hide and seek with us finally become visible, like black holes. There's also a mind-blowing idea called gravitational waves. Einstein predicted their existence tens of years ago, but only recently have we finally been able to confirm them. And that was a huge breakthrough in the science world. These waves carry the echoes of cataclysmic cosmic events, such as the collision of massive black holes or the birth of newborn stars. Just like dropping a pebble into a serene pond, these crazy events cause a ripple effect. But instead of water, it's space-time itself that ripples and warps. Scientists have just recently developed a way to listen to these whispers. They've created instruments capable of detecting these gravitational waves. These instruments, known as interferometers, are like ears that are finely tuned to catch the subtle vibrations of the universe. But one thing's for sure, gravity is a superstar that shapes our universe. It keeps everything around us connected and rules our entire universe. The quest to unveil its ultimate secrets continues, and it's a thrilling adventure for scientists and curious minds alike.
Legend has it that in the 17th century, Sir Isaac Newton noticed an apple fall from a tree and began wondering why the fruit had fallen to the ground and not upward or sideways. Well, that would be freaky. After years of studying, he concluded that gravity must be the culprit. The scientists called it a force of attraction that existed between all objects. But it was Albert Einstein, many years later, that revolutionized these ideas about gravity. Legend also has it that he wasn't completely satisfied with Newton's findings. Something just didn't seem right. As a young scientist, Einstein had some trouble formulating his theories, trying to explain the behavior of moving objects. When an experiment came to his mind, he called it the happiest of thoughts. Gravity feels like the sensation of riding in an ascending elevator. He called it general relativity. Einstein began working tirelessly, trying to prove this idea. At one point, he even complained he was on the brink of losing his mind. Now, in the simplest terms, general relativity claims that gravity is the curvature or warping of space. The greater mass an object has, the more it warps the space around it. Imagine a heavy ball resting on a trampoline. The rubber sheet under it gets warped under its weight. It's the same with our sun. It's big enough to twist space across the entire solar system. That's why our planet, as well as all the others, orbit around the star. This warping also impacts how we measure time. If you look at your watch, time seems to go by at the same rate every day. But if you hike to the top of a mountain and your friend wanders through a valley at the bottom of this mountain, you'll see that your watches will calculate time differently. One watch will tick faster, while the hands of the second one, which is traveling through the valley, will move more slowly. That's because gravity affects how fast time goes by. With these experiments in mind, Einstein concluded that gravity was not a force of attraction, but rather a curvature in the fabric of space-time. We feel gravity as a force simply because we're placed on some surface. If there was no surface and no attraction between us and this surface, we would become weightless. If you don't mind getting some weird looks, try this experiment. You'll need a bathroom scale and an elevator to ride. You'll soon see that your weight fluctuates as you move up and down in the building in the elevator. The gravitational force is the same, but your weight is different because the elevator speeds up and slows down. Aboard the International Space Station, astronauts literally move along with the station, so there's nothing to push them against the side of the station so that they have some weight. Even if we still think of gravity as a force, it's the weakest one we know. First of all, it only attracts. There's no negative counterpart that could push things away. And weirdly, even though this force is strong enough to keep galaxies together, we still overcome it every day. Every time you lift an object off the floor, you overcome the force of gravity produced by the entire Earth. Ooh! Just to paint a better picture, Earth's gravitational pull is weaker than the power of a refrigerator magnet. The fact that our planet has gravity also affects the way we look and act. All creatures on Earth are limited in growth by the height of their skeleton and by how much weight it can carry, which is directly proportional to gravity. That's why some marine creatures can grow bigger. The largest animal on our planet right now is the Antarctic blue whale. It's about the size of 2 school buses combined. That's because sea creatures can float, which slightly counteracts gravity. The effects of gravity can be seen in people, too. We are taller in the morning than we are in the evening. Our everyday activities and the added effect of gravity make the cartilage in our ankles, knees, hips, back, and neck compress. Once you have overnight rest, the cartilage swells back to normal. Gravity might also affect your shower routine. That is, if you're an astronaut. They have to rely on the old-fashioned way of bathing up there on the space station. They can't take a shower since the force of gravity up there is different and water doesn't flow as it should. Instead, they use liquid soap, water, and no-rinse shampoo. They first squeeze some liquid soap and water from pre-made water pouches onto their skin. Next, they open the no-rinse shampoo and add a little water to wash their hair. Towels are then used to wipe off the excess water, which is really precious in space. To make sure they recycle it, an airflow system quickly evaporates excess water. Gravity and weight shouldn't be confused. Astronauts on the space station do float, and you may sometimes hear that they are in the state of zero gravity. It's far from the truth, though, since gravity up there is about 90% of its value on our planet. But astronauts look and feel weightless, since weight is the force a certain object exerts on them back on Earth. Most creatures have evolved to sense and adapt to Earth's gravitational pull. In the sea, for instance, some fish have floating calcium carbonate deposits in their heads. Scientists call them ear stones, and they're pulled down by gravity. They act like a fish's internal compass. Now, plants have evolved to grow starch grains in the tips of their roots. They use this amazing feature to force their roots deep down into the soil. As little as we seem to understand it these days, we do need gravity for way more things than we can imagine. For instance, some bacteria become even more dangerous in space where there's little to no gravity. Salmonella, for example, the type of bacteria that is known to cause food poisoning, becomes 3 times nastier in the condition of microgravity. So you really gotta cook your chicken. Our own moon stays where it is because of the effects of gravity, too. If it weren't for this force, our satellite would have floated away by now. But it's held in place by Earth's gravitational pull. Objects with the biggest gravitational pulls in the universe are black holes. Thankfully, our planet is really far away from any of them. Nothing can escape the gravitational pull of a black hole, not even light itself. Similarly, gravity is different on each planet, and because of that, things weigh differently depending on which planet they're on. Take Earth, for example. An object that weighs 100 pounds here would only be 38 pounds on Mercury. But if you're planning on losing weight fast, try booking a trip to Pluto. Someone who weighs 150 pounds on Earth would weigh no more than 10 pounds on Pluto. The same person would weigh considerably more on Jupiter, which is the planet with the most powerful gravity. 150 pounds on Earth would turn into more than 354 pounds there. No thanks. Remember that experiment with watches ticking at different levels of elevation? It turns out that gravity isn't spread evenly on the surface of Earth. Why? Because our planet isn't a perfect sphere. The mass of Earth isn't evenly distributed either. That's why you get variations in gravity in different locations. More so, gravity is weaker at the equator because of the centrifugal forces produced by the planet's rotation. Since we've always perceived gravity as a force, we seem to believe that it has somewhat of a suction motion. But it's not exactly true. Back in 1998, scientists were baffled to see that the expansion of the universe was speeding up. So they linked this to the repulsive gravity of mysterious dark energy. We now know that dark energy makes up for more than 60% of the mass energy of our whole universe. But since nobody knows what it actually is, we can only make assumptions. And one that's largely accepted is quantum theory, which seems to claim that gravity pushes rather than pulls things in. You got all that? I may need to watch this one again.
1.5 feet with the Earth's gravity. Verification complete. Now the simulation room will recreate Mercury.
It's so hot in here.
Yes, it's like standing next to a volcano. Your jump is 4 feet high. Now switch to Venus.
Wow, this place looks scary.
On the real Venus, everything is toxic.
I feel no difference.
Yes, the gravity here is almost the same as on Earth. Switch to the Moon. Gravity on the Moon is 10 times lighter than Earth's, 9 feet. The next one is Mars.
Huh? It's pretty comfortable here.
The gravity here is the same as on Mercury. 4 feet. Now, prepare for the struggle.
Huh? What do you...
There is no solid surface on Jupiter. Although Jupiter is a great deal larger in size, its surface gravity is just 2.4 times that of the surface gravity of Earth.
It's hard to even stand here.
Only half a foot. Got it. Switch to Saturn. There is no solid surface here either, but Saturn's gravity is almost the same as Earth's. Now Uranus.
It's so cold.
It's 5 times warmer here than on the real Uranus.
Seriously? My legs are numb.
1.7 feet. Gravity is slightly weaker than Earth's. That's Neptune for you. Your jumps are 1.3 feet high. Gravity is slightly stronger than Earth's.
Get me out of here.
Turn off the...
Okay, picture this. In the not-too-distant future, you're heading out on a space vacation, and you need to decide which items are worth bringing along. But instead of checking the weather forecast, you open a gravity simulator. That's because you need to know how each object will behave on different planets. For instance, should you take this metal shovel with you or not? Well, according to your itinerary, it's going to be a long trip. You're planning to visit every planet in the solar system and even a few moons. But due to the difference in gravity on these space bodies, you're not sure how useful some of the objects you're going to bring along will be. Well, let's start with the basics. Tupperware. I don't know about other space travelers, but us Earthlings carry our Tupperware around everywhere we go. And still, if you were to transport it to, let's say Mercury, it would most likely fly away into the atmosphere. These plastic containers you use to keep your food are too light. And since the gravity on Mercury is 2.5 times weaker as gravity on Earth, well, maybe you'll have to fill your plastic containers up before taking them out of your spaceship to have a picnic. If a Tupperware container weighs about 0.5 pound on Earth, It'll weigh just a quarter of that on Mercury. Now, if we add some bananas, a handful of baby carrots, and 2 watermelons, then it'll be safe to carry it out of your space vehicle. You'll just have some difficulty making it all fit in a standard-sized container. But wait! Before you do that, you should know that the atmospheric temperature on Mercury can reach up to 800 degrees Fahrenheit. This means that any plastic container will instantly melt as soon as it gets in contact with the air. It'll burn up all the food, too. You can probably try taking a titanium container, that will work, or just stick to astronaut food. Now, shall we say Venus? Okay, Venus. If you were to take the same empty container to Venus, it would behave similarly to how it does on Earth. This is because Venus is also known as our planet's twin. These two have much in common. For example, almost the same size and mass. And when the topic is gravity, the formula goes like this. The bigger the mass and the greater the density, the stronger the gravity. Venus's gravity is approximately 10% weaker than Earth's. So, yes, you may leave your spaceship with your container, empty or full, and enjoy a beautiful and scenic lunch on the surface of Venus. Now, you'll have to figure out a way to eat without taking your spacesuit off, though. The atmosphere of Venus is filled with sulfuric acid, which can irritate your nose and throat and cause difficulties in breathing. Or worse. Much worse. Now, you'll have to forget about taking anything too light outside on Phobos. A little hint for you, it's not a Greek island, not even Greek yogurt, although it's a cool name. It's actually one of Mars's moons. Here, even your spacecraft would need a little extra help to keep close to the ground. If it weighed as much as a school bus, any regular-sized person could pick it up with just one hand. This is because on Phobos, the inhabitants of Earth barely feel the weight of gravity. And be very careful when jumping around because one leap and you may fly straight into outer space.
Passengers on board the Voyager spaceship, please keep your arms and legs inside the vehicle at all times.
Well, you're approaching Jupiter, a gas giant. A never-ending storm is raging in its atmosphere. Plus, there's no solid surface there, which means no landing for you on this planet. If you look out the window, it might seem that you are moving through a giant cloud. But for the purpose of your experiment, it'll work just fine. Try throwing into the air that baseball you brought along in case you get bored of all the space travel. And measure the time it'll take the ball to hit the surface. If on Earth, the ball will fall at a speed of 32,174 feet per second. On Jupiter, the same ball will hit the ground at a speed 2.5 times greater than that. That's because Jupiter is more than 10 times as large as Earth and around 300 times as heavy as our blue planet. Now, if you move your spaceship just a little bit to the side, to one of Jupiter's moons, Europa, the situation will be completely different. Throwing a baseball in the air on Europa will mean never seeing it again. Gravity there is almost non-existent, which means that not only a baseball, but even a grown-up person can fly away any second. Now, on the other hand, if you decided to venture out of the spacecraft to explore Europa's gravitational field, why not try to lift the space vehicle itself? On Europa, a regular Earthling can easily lift up to 1,000 pounds, which is the equivalent of a full-size male moose. Or you can lift a pyramid-like formation of 9 regular people. The choice is yours. When approaching Saturn, be careful. While from afar, Saturn's rings look smooth and solid. From up close, you'll notice that they're made of chunks of ice and rocks floating in space. You won't want to have your spacecraft anywhere near those. There's also no solid surface on Saturn, which makes landing impossible. And the atmosphere is full of ammonia. Keep in mind that it's a pretty inhospitable environment for a human. Now, inside the spaceship, you find a collection of sci-fi books, enough to fill an entire bookshelf. Altogether, they must weigh around 400 pounds. Yep, that many books. And like someone with a superpower, you try to lift over 200 pounds of weight at a time. But guess what? You fail, because Saturn's gravity is too similar to that on Earth. Now, in case you got confused with all this gravity talk, when we're measuring gravity, we're speaking about the power of the force by which a planet or other space body pulls objects toward its center. So, if you need some help in organizing that sci-fi collection in alphabetical order, asked the crew to move the spaceship to a neighboring space body with a weaker gravitational pull, like Pluto. These days, it's not considered a planet anymore, just a dwarf planet and one of the furthest from the Sun's space bodies. You'll need an extra warm spacesuit to wear there. Pluto is freezing cold and has a tiny surface. It's smaller than Earth's moon. But it's a great place to test your strength. If on Earth it's kind of impossible for a regular person to lift an elephant, on Pluto you'll be able to pick up a baby elephant weighing around 265 pounds, or even a medium-sized elephant that can be as heavy as 2,000 pounds. On your way back to Earth, you make a pit stop on Uranus. The coldest planet in our solar system has an average temperature of around minus 350 degrees Fahrenheit. So, if you attempt to get out of the spacecraft, you'll freeze mid-movement. Although gravity on Uranus is pretty similar to that on Earth, there's one thing that's very different: time. A 2-week getaway on Earth turns into a 3-year-long vacation on Uranus. Now, when you get sick of cold planets, you can travel back to warmer ones. Okay, now, Mars is definitely warmer than Uranus, but its average temperature is still about minus 81 degrees. On Earth, we only have such low temperatures at the South Pole during the winter. When you land on Mars, you'll start to feel light and strong at the same time. Mars's gravity is about 2.5 times weaker than that on Earth. So, in other words, you'll probably manage to lift your own body weight without any difficulty. So, all those handstands you've been dreaming of doing, you've found a place to fulfill your dream.